1.5, classifying real numbers. Your real numbers are made up of both the rational numbers and the irrational numbers. In this green box here, we have all of the rational numbers. First, we have the natural number set, which starts out with 1. There's no decimals, no fractions, no negative numbers. The way I like to remember this is it's natural to start learning how to count starting with 1. You don't start with -2 or -3. So that's an easy way to remember natural numbers. The only difference between the natural numbers and whole numbers is one single number. It's the number 0. An easy way to remember that the whole numbers are just the natural numbers plus the number 0 is that in the word whole, you can think of the O as a 0. Integers are all of your whole numbers plus the opposite. So the opposite of negative, or opposite of 1 is -1, opposite of 2 is -2, etc. So those are all your integers. Your rational numbers, you need to be able to determine a rational number 2 ways. Basically, they're going to be in fraction form or they're going to be in decimal form. For a rational number, you can think of a ratio. That's the first 5 letters of the word rational, says ratio. It's basically any integer over any integer. Now, again, remember that they have 2 forms though. They have the fraction form or your decimal form. So 1/2 is 0.5, -1/3 is -0.333. So it just repeats with the 3's. 9/11 as decimal form is 0.81, 81, 81, 81, 81. When you have the bar over there, that just means whatever the bar is over, that's repeating. So, and then if you just have a regular number 20, which is, of course, an integer and a whole number and a natural number, if you just put that in fraction form over 1, it makes it a ratio of an integer over an integer. And if it's not in fraction form, it's just 20. So remember, all of these integers you can put over 1, which makes them a ratio. So all of these numbers are considered rational, all of these here. Now, as far as your decimal form, they either stop or have the same repeating pattern. It can't have any pattern. It has to repeat the same thing over and over. So for example, here 81 is being repeated over and over. 81, 81. Now for your irrational numbers, you just got to remember that they are the opposite of rational because the prefix "ir" means not. So what is the opposite of rational? Well, what's the opposite of stopping? That means it goes on forever. What's the opposite of having the same repeating pattern? It's never having the same repeating pattern. So these go on forever and never have the same repeating pattern. A perfect example is pi. Now, anytime you have a radical that is not a perfect square or a perfect cube or a perfect fourth, when you put that into the calculator, you're going to get a decimal that will go on and on forever and will not have a repeating pattern. So that is also considered irrational. Your square root of 4, that's just 2. So that's just going to be rational. Now the square root of a -4, what times itself will give you -4? Oh, you have to have an imaginary number. That's a whole nother number set, and we don't have to worry about this for this class. Determine which numbers are rational or irrational. So remember, we have our decimal form and our fraction form. This one is in decimal form, and it looks like it does go on forever. Does it have the same repeating pattern? No, it doesn't have the same repeating pattern. So you got to think of pi, because pi is a good example of what is an irrational number, and we're all familiar with pi. It goes on and on forever, has no repeating pattern. So this is irrational. Now, negative 89, we could put that over 1, so that's a ratio. So that is rational. You can see the word ratio in there. Also, all of your rational numbers include your integers, which are your whole numbers and their opposites. And the opposite of a positive 89 is negative 89. Here, square root of 49, that square root of 49 is just a perfect square. So that means the root or base for the square root of 49 is just positive 7. So if we wanted to make it into a ratio, you can just put it over 1, so that's rational. You don't have to do this part. I'm just showing it in fraction form. Okay, here, this is in decimal form, and it stops. So anytime it's in decimal form and it stops or has the same repeating pattern, that means it is rational. Because that's not like pi. Pi goes on forever and has no repeating pattern. Now the square root of 5, this is not a perfect square. So if you were to put this in your calculator, you would get, well, 2 squared is 4 and 3 squared is 9. So you would get 2 point something. And it would go on and on forever and have no repeating pattern, just like pi. So this is irrational. Now this one is in decimal form and it has a bar over the 212. So that means 212 is repeating over and over and over. So if it has the same repeating pattern, then that means it's rational. Down here, we're writing 9.279 as a ratio of 2 integers. Since 9 is a whole number part, this is your decimal part. And this is to the thousands, that's tens, hundreds, thousands. So you can write that as 279 thousandths. So we have 9 wholes and 279 thousandths. Then we'll convert to an improper fraction. So we have 9 wholes cut into 1,000 pieces. So 9 times 1,000 is 9,000. Add the 279 pieces. That'd be 9,279 thousandths. So there it is written as the ratio of 2 integers. Write 3.25 as a ratio of 2 integers. So what we have is 3 wholes and 25 hundredths. Then we convert this to the improper fraction like this one. So 3 wholes cut up into 100 pieces would be 300 plus the 25 pieces we already have, which would be 325 hundredths. Then we can reduce this fraction by dividing by 25 to the numerator and dividing by 25 to the denominator. You can only reduce fractions like this if what you do to the numerator, you also do to the denominator. It works with dividing and multiplying, never adding or subtracting. So divide by 25 here, and you end up getting 13 over 4.